Okay, we'll go ahead and get started. A couple announcements. Your textbook and this workbook are located in Canvas through the course materials page. So you click on there, click again. It should launch another thing called Vital Source or G2 or something like that. So those things are electronic, and you do have to opt in through the Eagle First Aid program or whatever it's called. If you don't sign up for that, I think you lose access in like a week or two. The other route you can take is buying this stuff, where you actually see the cost of it. So they're pretty expensive. If it's baked into the first aid, you're just in your tuition somehow, and you never see the cost. The other thing is, this is the only physical resource that the bookstore sells. That's a required material, so you have to actually go there and buy this. This is the study guide for the final exam. So it's broken up into semester 1 and 2. So if you take Organic 2, you can use it for that course as well. Within each sort of unit or module in here, there's practice questions with explanations. And then there's study questions you can do. I would encourage you to start using this now so that you understand the format of the final exam and you don't feel like you got hit by a truck when you actually see it. Yeah.
I have the actually go
So I will neither endorse nor refute that, but yeah, you can use whatever version you have. I like these things because you can write in them. The course textbook is Organic Chemistry by Wade, but this is a workbook that's really just problems. So this is by David Klein at Johns Hopkins. Organic chemistry is a second language, and the primary focus of this is to do problems and develop an intuition for being successful. So make sure that you're aware of these things, and again, you actually use them. It's important. I uploaded an Excel file in Canvas. Did anyone download that yet? One or two people. You actually have to download it to use it. So you download it, it will launch Excel. Then you can start punching your points in there, and it will calculate your grade based on the number of assessments that have been doled out so far. So again, that's not the grade you're ending up with in the semester. It's just whatever point in time. And then the final announcement here, make sure that you can access your ZipGrade account. For those of you that cannot find your ZipGrade access code, anyone that found it, how did you find it?
In the dashboard, it's under assignments.
So I think the main issue is, unlike everyone else, I do a lot of stuff on my phone. So the Canvas app, in my opinion, does not look like Canvas on a web browser. So if you're not seeing stuff on the app, just use the browser, and then you might see other parts of the window or something. So they're in the comments under that assignment, and that's how you access the ZipGrade. And that's important because when you do take your online exams in ZipGrade, please do not take them on your phone or tablet. You will have a miserable experience. Make sure you're using a web browser so that you sort of see everything that's visible there. The phone or the tablet isn't going to show things, and there'll be structures and stuff that you have to look at, and if you have to constantly pinch to zoom and stuff like that, you're going to waste time doing that sort of thing. Any questions about course mechanics or anything like that before we get started? Okay, seeing none, let's move on. So I'll talk a little bit about the periodic table and the elements, the building blocks or ingredients that are useful for us in this course, and how the information in the periodic table can be used to logically build molecules. So we're all familiar with the periodic table at this point. A couple of things I want to point out in terms of like directions. So groups go up and down. And so that's signified by, what are these Roman numerals or these Arabic numerals here. Notice if in the Arabic it's 1, 2, 3, 4, then it goes up to like 13, 14. We want to use the Roman numerals when we're talking about the elements we're interested in. So group 1, 2, and then 3, 4, 5, 6, and 7. So those numbers are important. They'll tell us things about how the elements in those groups bond. The other important thing about groups in terms of the reactivity, so say for example, because this is organic chemistry and we're talking about carbon primarily, so below that silicon, then germanium, tin, and lead, elements in the same group have similar reactivity. That's important to know. So on the horizontal are the periods. So those move left, right. And so the numbers that we need to be aware of here are just the atomic numbers. So hydrogen starts at 1. Then we get to helium 2. So that's period 1 or row 1. Then we go back over to the left in period 2. We're at 3, lithium, and then we move up. So say, for example, carbon is atomic number 6. What's another sort of fact associated with atomic number in terms of counting? Well, not protons, electrons. So it's the electron count. And the reason that's important is because the electrons are what does the bonding in chemical reactions. So for the most part, we're not terribly concerned about protons and neutrons at this point. It does play a little bit of a factor in this course, but mainly it's the electron count. So we have 6, we have the letter C, that's the carbon, and then we have 12, which is the atomic mass unit. So we're going to use kind of mass and weight interchangeably for different purposes in this course, but understand how mass and then the atomic number are related. So that's when you get into the proton and neutron counting. The other thing I want to talk about in terms of the elements are isotopes. Does anyone know what an isotope is? So it's a lot of those things together, sort of that you're looking at the same atomic number of that element, but the mass is changing due to the number of neutrons. So we're going to look at mainly what are called stable isotopes. So there's stable versus radioactive. So we're not concerned too much with radioactive ones, but with stable ones. So for example, if we consider hydrogen, does anyone know an isotope of hydrogen? Deuterium. So deuterium, and then tritium's the radioactive one. And then what are two isotopes of carbon? Carbon-13 and carbon-14. So which one's the radioactive one? Carbon-14. So the isotopes are important for a form of spectroscopy. So hydrogen is atomic number 1. Carbon's atomic number, or we're going to use the mass here, mass 12. So carbon-13, that's an odd number. 1 and 13 are odd numbers. And that has a special implication in terms of the nucleus that we can observe in a phenomenon called NMR. Do you know what that stands for? NMR? Nuclear magnetic resonance. Has anyone ever had an MRI? I've had 2. What's MRI stand for? So magnetic resonance imaging. It's the same thing. An MRI instrument is like a big donut. There's a magnet in it. They don't use the word nuclear because they don't want people to think they're being irradiated with stuff, but in the word MRI is imaging. And so what do doctors use MRIs for? To see what? To see organs? Why wouldn't you use an X-ray?
Because X-rays give you radiation.
So X-rays show bones. It doesn't show soft tissue in the detail that's needed. So a medical doctor would want to use an MRI to see what's going wrong with an organ or soft tissue. Like we live in a technological age, so this is a phone, but it's a camera, a computer. We don't want to cut someone open to see if like they have a liver laceration or something. You want a machine to do that. So the machine will tell you what's inside the body. An NMR will do the same thing. So of a substance you have, you make a sample, you put it in an NMR, it's going to tell you information about the connectivity of the elements present. So we'll talk a little bit conceptually about that today under a concept called symmetry, where we look at molecular formulas and structures and how we can use that to understand the product of a reaction is this and not something else. So as I said, we're going to mainly deal with the chemistry of carbon and derivatives of carbon. So the stuff that's bonded to carbon is called a functional group. A functional group is a discrete collection of elements with a very specific bonding pattern. It's then going to have some name. The name of that functional group is how do we know a functional group's in a molecule? That's when we start using analytical techniques like NMR and other things we'll talk about. So there's going to be a little bit of discussion of physics in this class, not too much with equations, but more with light. So we can all look up and see the light. But I mentioned X-rays a couple minutes ago. X-rays are a form of light. So on the electromagnetic spectrum, there's different wavelengths of light. And the light in those different regions will interact with molecules differently and give us signatures of what functional groups are present. So from that data, we can then piece things together. So the group number here, again, the groups were up and down. The reason I like using these Roman numerals is that it actually tells us the number of valence electrons. So while the atomic number of carbon is 6, the number of valence electrons is 4, and that's directly related to that group number. And the reason that's important is because of the 6 electrons total, only 4 of them are used in bonding. What are the other 2 called? What do you think? Core electrons. The core electrons, if you remember from electron configurations, those kind of go back up into the prior period, and they're called the Nobel gas configuration. So the 6 minus the 4 is 2. Those 2 are not used in bonding. So the atomic number, that was our total number of electrons. C is the element. And then 12 is the mass. When you do calculations in this class, as kind of we'll see a little bit today, we only really need to use these numbers here. We don't need to go past the decimal. There's another analytical technique we'll learn called mass spectrometry. Any forensics majors in the crowd? So mass spectrometry is important for forensics because you can increase the number of decimal points here. You can get out to like 4 or 6. And then what that allows a scientist or analyst to do is really zero in on a molecular formula. Any student athletes in the crowd? Couple? If you don't mind me asking, do you have to submit urine samples? You do?
Yeah.
And so what are they looking for in those urine samples? So they're probably looking for performance-enhancing drugs of some sort. And so the way they can determine if it's there or quantify it is through mass spectrometry. So when we get into Module 2, we'll talk about a common example of, like, say, Lance Armstrong. He was doping with human growth hormone or something, but say it was just testosterone. The human body, male or female, produces testosterone. The molecular formula of that has a certain composition that will translate to the mass. If someone is taking synthetic testosterone, there will be a slight difference in the mass number in these decimals out here. And from a submitted sample to the average sort of normal human, you can tell if someone's doping. Or if they're winning the gold medal all the time, you can suspect some things. So let me just preface this by a lot of students don't like my tables. I like to learn from tables because it helps me to see the trends and the things that we have to use to solve problems. So I'm going to go through this and then explain what each little bit is useful for. So the cropped version of the periodic table, that's really the elements that we need to consider for this course. The noble gases we're not worried about, but everything else you see, those are the building blocks we'll use. And I want to focus specifically on hydrogen. You can be 100% confident that every molecule we talk about is going to have hydrogen in it. So that's a valid assumption. So there's the hydrogen, and then the rest of these are in period 2, CNOF. So those are the main building blocks we'll talk about. So we have our element, and then here's our electron configuration. So hydrogen atomic number 1. So there's 1 electron. So look at helium, we're just adding a number. That's going to have 2 electrons, then we get down to lithium 3, beryllium 4, boron 5. See this group 3? We'll talk about some of those elements as we progress through the modules, but there's something unique or maybe weird about them. We'll focus on what that is later on. But once we get past that, everything sort of is normal and obeys the octet rule. So 6. Carbon has 6 electrons, so let's count them. 1s2, that's filled, right? So each orbital gets 2 electrons. And what do those electrons have to be? So spin up or spin down, however you want to think about spin plus, spin minus. They have to be spin paired. Then we get into the second period. So this is period 2, the s orbital. What shape is an s orbital? A sphere. 2s2, it's filled. And now look at this weird letter here. This changes because the nature of the orbital then changes to p, because we sort of hop over all this stuff, the transition metals. We hop over that into here, and it says 2p2. What's the shape of a p orbital?
A dumbbell?
A dumbbell shaped. Look at that for nitrogen, 2p3. What's going on there? How many different p orbitals are there? There's 3. And so what's the relationship of those orbitals to each other in terms of space? They're on different axes, so x, y, and z. So we could actually say that's p sub x, p sub y, p sub z. So the difference between 2p2 and 2p3, these electrons here, they're not in the same p orbital. So what was the rule when you're filling? So you don't spin pair them until those degenerate orbitals are all filled. So if, again, look at the count, 2, 4, 6, and then these just add 1 to those p orbitals. So the group number, as I said, we're going to use those Roman numerals, group 1, group 4. So carbon, group 4. Again, why is that important? The 2s2 and the 2p2, those are the valence electrons. That's 4 electrons. Those are the electrons that are used in bonding. So 4 electrons, carbon forms 4 bonds. Do you know what a carbon with 5 bonds is called? Who's from Texas? A couple people. A carbon with 5 bonds is called a Texas carbon. Why? Because everything's big in Texas, or the state flag of Texas has a 5-pointed star. So again, let me just point this out in terms of the intuition. If you draw a structure and it has 5 bonds to it, it's wrong. So you have to reconsider the rules and what you're proposing. So 4 bonds, a bond has 2 electrons, so 4 times 2 is 8. That's the octet rule. Carbon has no lone pairs. Nitrogen, it's an odd number now, 5, in terms of the valence electrons. So what happens is nitrogen forms 3 bonds. So that gets you to 6 electrons. You have 2 left over, so it's always going to have a lone pair. So what you can see in these parallel trends about bonds versus lone pairs is they run opposite. 4, 3, 2, 1, 0, 1, 2, 3. The other thing I want to point out, the molecules are always going to have carbon and hydrogen. That's a valid assumption. The presence of any other elements is what we have to use the spectroscopic methods to determine. The other elements I'm going to refer generally to as heteroatoms. So hetero means different. So anything that's not carbon and hydrogen is a heteroatom. And part of the development of your chemical intuition in this course is, how do we know NOF or some other heteroatom is in a molecule? So as a fact, I'm telling you, carbon and hydrogen are there. They're there. But what about these other reactions that have heteroatoms? How do we know they're there? We have to use analytical instrumentation to determine specific signatures or fingerprints of those heteroatoms. The bottom part of the table there, I've just shuffled it up, and then I've added some more rows here. So we're going to start building some stuff. We kind of already started this on Monday. We're going to build these molecules, and then we're going to sort of fill in some information. Any sort of data, like physical data, I don't expect you to memorize. The exams are online. You can look shit up and find it on Google. So don't worry about that sort of stuff. I mean, I'll even give you websites that you can navigate to find things. The point, again, of the exam is for you to apply what you know and see if you can solve something you haven't seen before. So by filling in this data, what we want to do is identify the trends in how the bonding relationships affect the physical properties. So let me just use the model kit here and build some stuff. I won't write too much on this slide, but so we know that hydrogen has 1 electron. So in this kit, so these are called snatoms. So that just means snappable atoms. The white ball is a hydrogen. It's kind of hard to see, but there's a little silver ball in there. It's a magnet. So that ball is meant to represent the 1 electron of hydrogen. So I have one of these, and I snap them together. So this is hydrogen atom. That's H2, hydrogen molecule. So it's, any questions on that? Some other things I want to talk about. You have your own model kits, correct? Please open them up and use them. There will be students that come into the last lecture of a semester and say, like, what do I do with this? It's like, you open it and use it. The reason you want to use these kits is it's a tool to help you visualize. When I write stuff on here, it's flat, and the molecules are not flat. You have to visualize them in 3D to understand the chemical reactions that are going to happen. And again, there's a lot of different learning layers, like lasagna in this class. It's not only the content, but how you visualize things. And from your reference point to mine, if I start twisting and doing these rotations and flips, things look different. And when you see a molecule that's flat, you might not understand how a reaction is happening. So this is H2. What shape would you call this? Linear. So we're just going to go across and make this second thing methane. So the black ball here is carbon. There's 4 faces to it. And we said that carbon forms 4 bonds. So that means we need 4 of these. And so that's now methane. What shape is this again? Tetrahedral. So hydrogen, methane, now we want to do ammonia. So remember that this was the weird one because of that lone pair. This model kit does not show lone pairs. So when I put the 3 hydrogens on, if you see like the methane versus ammonia, notice there's nothing up here. That's where your mind has to visualize there's a lone pair. So the ammonia kind of sits like that, but the name of this, in terms of the shape, is different. Remember what that name's called? Trigonal pyramidal. And the reason the name changes is because I'm going to use some words interchangeably here, like valence or ligand. So carbon has 4 ligands. The ligands are hydrogen. The nitrogen has 3 ligands, and then a lone pair. There's 4 things there, but one is a lone pair. So the reason this is not called tetrahedral is because it doesn't have an actual element or atom in that 4th position. So our water molecule, so we're going 4, 3, and now 2 valences. So that's H2O. And then what shape was this? Bent. And so now notice the open space here. You have to visualize like 2 lone pairs coming off that. And then our fluorine HF, there's just 1 bond and then 3 lone pairs. And so this is also linear. So again, I guess my teaching philosophy for in general in this course is, by the end of organic 1, and then if you take organic 2, you should be able to look at any molecule drawn, no matter how complex it is, and understand all the information that's being told you just in that drawing. Any questions before we move on here? So this is kind of everything we just talked about. What we're doing here in this row of elements, I'm showing you the valence electron. So hydrogen was 1, carbon 4, nitrogen 3, and then the lone pair. Oxygen, 2 valence electrons, 2 lone pairs. Fluorine, 1 valence, 3 lone pairs. Then what we want to do is just, for every open valence, just shove in the number of hydrogens required. So 1 plus 1, that gets us our H2. And I've colored the electron red just to show you that it's coming from another atom. So we said on Monday, two electrons make a bond. The convention is to show that bond as a line. If I have to draw bonds with dots like this, I'll teach even slower than I am now. So all it is a convention. And what I want you to really understand about learning in this course, I assume, how many of you have your driver's license? So you learned how to drive. And so when you're on the road and you see a red sign, what do you do at a red? You stop. It's a learning convention. I mean, that sign could be purple, right? It's just the fact that, an amazing fact that a group of humans got together and agreed on something. We're going to make it this shape, this color, and it's going to have this behavior. And that's what these conventions are. So don't get too overwhelmed with things now. You kind of have to accept some facts, and then as we ask more questions, we'll understand the physical nature of what that bond means. What else do I want to say? One thing I do want to point out, so say for ammonia, NH3, like if I draw it in class, I might draw that, but I haven't put the lone pair in. It exists there, so understand that it's there. If I'm not drawing it, it's just out of a time constraint. And then the last thing on this slide is electronegativity, and that helps us determine if a molecule is polar or nonpolar. So the values in gray are the electronegativity values from the Pauling scale, and that's shown on another slide. So hydrogen's 2.2. So between these two elements, there's really no difference other than some sort of fleeting change in polarizability due to electron or nuclear movement. So that minus that is 0. There's no difference. Carbon is 2.55. Hydrogen was 2.3. So you get about a 0.3 difference. And again, they're fairly close, so that it's not that big a change in the electrostatic potential of the bond. So the Rubicon is right there. It's the line that we are going to cross. And if we look at nitrogen, now it's 3. So the difference between that 3 and 2.2, now you're past this threshold where the bond is polarized. And because there is a lone pair, we can say, well, that nitrogen's delta minus. The hydrogens are all delta plus. And so once we do that, we can then draw a bond dipole. And that's just an arrow showing how the bond is polarized. So you start with kind of a cross, and then the arrow points to the delta negative. So that may seem like, yeah, no shit, who cares? But once you get those heteroatoms in a molecule, that is really what determines all of the reactions we're going to learn. That change in how the molecule is polarized will dictate every mechanism we learn. So what I've done here is for each molecule, I filled in the melting point in degrees C. Remember, when you want to think about this, because that number is like really negative, like negative in terms of the sign, not its personality. The lowest in degrees C is negative 273. So from there, you're marching towards zero. So negative 273 to negative 259, hydrogen's a solid. So then from negative 259 to negative 253, it's the liquid. So there are certain ranges in which those solids and liquids exist. At room temp 25, it's a gas. There's no dipole moment because there's no change in electronegativity values. So these other numbers, as I said, that's just data that we can pull from the internet. Notice now for the dipole moment of ammonia, the dipole moment, that's referring to the entire molecule itself. So you add all the individual bond dipoles, add them up with some vector math, and you get a bond dipole. So there's some trends we can talk about why this number increases. And then I mentioned functional groups. Hydrogen's a molecule by itself. It doesn't really have any sort of other functional groups attached to it. Methane is an alkane. See how that ends in ANE? And then methane ends in ANE. So my name's Matt. You know, other than you physically seeing me, you can describe things about me, but like you don't know anything else about me. The names in organic chemistry tell you a lot. So ANE tells you it's a hydrocarbon. The meth, not the drug, the METH part, tells you it's one carbon. The other thing the name is telling you is the type of carbon in there in terms of hybridization. So alkanes have sp3 hybridized carbon. There's another functional group called alkenes. They have sp2. Alkynes have sp. So there's stuff you can pull out of that name that you want to make associations with. Ammonia, the molecule, can be classified as an amine. So if you have carbon with, say, a nitrogen that has some hydrogens bonded to it, those are called amines. Anything with an OH group is called an alcohol. So I created a bonus assignment there in Canvas for you to take your model kit and make methanol. So what is methanol? It's an alcohol, but if you take a hydrogen from water and you substitute it with CH3, you've made methanol. You take an H off water, you substitute it with anything, you're making an alcohol. So HF is hydrogen fluoride. Remove that H, replace it with a carbon, you get alkyl halides. So I've called this an acid, but it should read alkyl halide. One thing I didn't fill in here was, see in green here, molecular weight. So we can do that together. So there's those molecules, and then you have your choices. And we want to figure out what are the molecular weights of each of those using the atomic masses shown. Which one can you eliminate right off the bat? What's another one you could possibly eliminate? What do we think the answer is? C. So C. Oop. So all we did was take the element, look at its atomic mass, and then multiply it by the proportions, and then add those numbers together. I don't have a lot of tips or tricks or hints or Easter eggs, but I do have one. See this number here? Based on everything else in that row, what's the difference of that number versus the other ones? It's odd. So if you see a molecule with an odd number of nitrogens, the mass of that molecule is going to be odd. So that's something you can tuck away in your brain, and we'll talk about the implications of that in Module 2. So now we've filled in those numbers, 2, 16, 17, 18, and 20. So what I want to do now, those are sort of the parents, the parent functional groups. Now I just want to build from what we've already made. So instead of adding like an H, we're going to add CH3. So we have we want to add that. So imagine we've taken methane, we've stripped off an H. That frees up a valence. So we want to add that to like each of those as they're shown. So for the first one, methane, we kind of already made that. I'm just going to take hydrogen, I added the CH3, we made that. So of the methane we already made before, I'm just taking an H off. And I want to substitute that H with this CH3. So we have one open spot, another open spot, and now that's a new molecule. So that's called ethane. So the prefix eth means two, and then A and E is alkane. So methane, ethane, and That's how we just build things. In the way that I like to think about it is like this H, I've substituted for CH3 now. I mean, I could build the next one up. If I take an H off here, so CH3, then I take an H off here, and that's a new molecule called propane. So for ammonia, I'm going to make my CH3 group. I'm going to take one of these H's off and then stick it on there. So you could think of this as a derivative of ammonia. So there's one carbon. A one carbon molecule is called methane. But this isn't methane anymore. So we sort of alter the name. This is called methylamine. So amine tells you the functional group. The first part, methyl, tells you the number of carbons. And then we'll do the same for the water, taking off an H, adding the methyl. This is called methanol. So you can't drink methanol unless you're destitute. So if I take an H off that and I add this, you know what that's called? So ethanol, or it's like a little dog. So ethanol is what's in beer, wine, liquor, spirits. Any of that stuff has ethanol. This tastes different, how it's made. You know, is it brewed, is it fermented, is it aged, that sort of thing. But this is alcohol. You can drink it, this is what gets you inebriated. And then finally, the HF, I take that off. I put that on there, and this is, well, flip the name around a little bit. This is called fluoromethane, or methyl fluoride. So there's a lot of different ways we'll communicate names based on nomenclature rules. And so this slide, maybe what I'll do is I'm going to leave it blank so you can fill in what we just demonstrated. What you're doing is taking that and then adding a CH3, just one CH3. So that fills it. Now if we take this, we're going to add just one CH3. Anything that's left over, you just add H. So that's going to make ethane. So for all of these, we're just adding a CH3 group. The remaining slots are H. So here are some ways of representing them. We're actually showing the electrons in each bond. We're showing the bonds as lines. And then down here, we're plugging in the electronegativity values. And then you can see that, we have methylamine. You have some bond dipoles here and here. So overall, this is going to be a polar molecule as well. Any questions? So the point I want to kind of bring back up is hopefully if you review these notes later on, that slide that showed the physical properties, of those sort of parent functional groups, water was really weird. Like it freezes and melts at 0, it boils and condenses at 100. But everything else, those values are a lot lower. And so you want to think about, why does the arrangement of elements in bonds in water give it those physical properties that are so different than methane or methylamine and that thing. That collection of functional groups impacts the physical properties. So what's sort of I'm not going to say rigorous quantitative description of nonpolar versus polar. And I have a boo-boo here. That should read polar. The table here shows you the Pauling electronegativity values. What I like to remember is that fluorine's the most electronegative. It's just call it 4. Anything else is going to be less than that. So when you're looking at a bond and then the change in that electronegativity value, if it's less than 0.4, then we say that the bond's nonpolar, and then you have to add all that crap up and then ultimately determine is the molecule itself polar. So when you're in this range here, 0.4 to 2, that's polar. Anything beyond that is going to be an ionic bond. So that's when you have the stuff that's on the far right and the far left of the periodic table coming together as a cation and an anion. So the things we're talking about now are covalent bonds. Are they nonpolar or polar? So there's the physical properties for those molecules. I've put these numbers in for the weights. You should convince yourself that you know how to do that based on the molecular formula. One thing I do want to throw out there is sort of like a learning grenade. So structurally, if you're given that, CH3, knowing the elements and their proportions and the atomic masses, you can calculate that. But say I just said, propose a molecular formula for an unknown substance with a mass of 30 grams per mole, and you're not given the structure. How can you take the number and then convert it back into a molecular formula? So that's more of like module 2 stuff, but see if you can think of a rational way of doing that without pulling your hair out. So we'll run through this slide pretty quick, but the take-home point is the bonding arrangements of those elements make functional groups that impact the physical properties. And we want to develop an understanding of why that is. So on the temperature scale here, we have Celsius and Kelvin. The red arrow is meant to be heat is being added into a system. The blue arrow means heat is being taken out. So another thing you want to sort of get straight with your mind in thinking about this, heat transfers, cold does not. So even though as humans we say, I feel cold, I'm wearing a sweatshirt, don't think I'm weird. The AC in the office I work in makes my hands freeze and then I get very uncomfortable. That's why I'm wearing a sweatshirt. So I say, I feel cold. But what is that? It's a lack of heat. Like, you can't transfer cold. You remove heat from something. So again, it's ways of thinking about stuff or concepts. So the point here is as we build these molecules, So we went from hydrogen up to methane to ethane to propane. There's the melting boiling point ranges. You'll see they slightly differ as you start adding stuff. So there's alkanes, amines, alcohols, fluorides. One thing I want to squash right now in this class and in your lab, don't ever use the response that, well, it's the weight is affecting the change in melting or boiling. It's really not a valid answer. It's the properties of those functional groups present that's changing the physical properties. So, as I said, most of you are biology majors or some other major, very few are chemistry, so why is this important? How many of you seen your physician recently? Did they prescribe you anything? So you got a prescription. It's electronic now. They don't give out the paper stuff, but then you went to CVS, Walgreens, or wherever, and then who did you interact with there? A pharmacist. And then what did the pharmacist do? Filled the prescription. They gave you what you're after. So that's the societal aspect. It's like, hey, I got a tummy ache. I need something. So you're getting a chemical. I mean, you call it a drug, but I mean, it's a chemical, and it's meant to do something to make you better. And those chemicals, they can come from natural sources called natural products, but mainly they're synthesized. So it's a synthetic compound. And so that molecule has specific functional groups that are going to target your ailment. And those functional groups are determined by the bonding patterns dictated by the periodic table. So from the atomic scale up into the global societal economic engine, I think organic chemistry is important, especially if you're going to become a doctor and you have the authority to prescribe drugs to people. You want to make sure that you're doing that in a very responsible manner, so that there's a thing called drug-drug interactions, so that the patient's taking two drugs or more, which is not uncommon. Those things don't fight each other inside the body, causing unwanted symptoms. Questions as I take a hit of Red Bull? Yep.
So for this upcoming test, what would you suggest that we hone in as far as module 0? So I was looking in there and I saw how to make an A and organic chemistry and then your paper and
So the module 0 exam really is a general chemistry review. It's meant, even though we haven't got too far into the course material yet, it's kind of some very straightforward questions based on a specific structure. Do you understand the conventions of the drawing? Can you count hydrogens? Can you figure out molecular formulas, molecular weights, that sort of thing? That's also meant to get you into zip grades so you know how to use it, and give you a feel of what the exams are going to be like. Yeah.
So what would you recommend studying for just for exam?
Maybe not that quite yet. I'll post an announcement in Canvas about some websites you can use. One of them is called PubChem, which is a database owned by the National Institutes of Health under their PubMed, National Institutes of Biomedical Sciences or whatever. But PubChem has pretty much every molecule known. And I'm going to leave it wide open. Just go in there and search for something. Look at a molecule. Do you understand the structure of that molecule? Can you count the carbons? Can you count the hydrogens, all the heteroatoms? How many lone pairs are there? That sort of thing. So we have 10 minutes left, and remember, you're paying for it, so I'm going to 12:15. One question. Does anyone know what movie that's from? War Games, exactly. So shall we play a game? I know this is serious for you. It's part of your major. It's going to influence your career and all that stuff, but I like to think of organic chemistry as a game, and the game is building stuff. There's just some simple rules we have to follow to make sure that we're not violating the rules. So the first functional group we're starting with, again, we're alkanes. And why do we start with them? Because the world runs on petroleum. So crude oil is the source of a lot of feedstock chemicals from which other things are made. So petroleum is a mixture of hydrocarbons. It's exactly that, hydrogen and carbon. And from that, reactions are acted upon those things to make other functional groups, and then down the road, you get that prescription drug that your pharmacist gave you. So prescription drugs do not grow on trees. They have to come from somewhere, and that's kind of what this exercise is about. How do we build them? So alkanes have a molecular formula of CnH2n plus 2. If I tell you to memorize anything in this course, it's memorize that. We're going to use it a lot. For any n number of carbons, you have 2n plus 2 number of hydrogens. So when n equals 1, 2, or 3, from that molecular formula, you can only draw one compound. When you get past 3 up into 4, you can draw more than one compound for that molecular formula. How do we do that? And how do we do that not violating any of the rules of the game? And then the subsequent questions which lead into Module 2, if a single molecular formula has the opportunity to produce more than one compound, do those compounds have the same name? Do they have the same properties? How do you differentiate them? There's different sort of prefixes we'll use for naming things as we go through here. So there's the buffet, there's the table we're going to eat from here. The first column is just the carbon count. So number of carbons, 1, 2, 3, and then I said once we get to 4, there's two possibilities we can draw for C4H10. C for 5 and 6, and I don't have it on here, but the ones that are listed, those are the parents. The parent names for that carbon count. So again, 1 through 4 is just memorize them: methane, ethane, propane, butane. Once you get to 5, then the prefix of the name actually tells you the carbon count. So pent is 5, hex is 6, and 7 would be heptane, not septane, so it's heptane. this is the molecular formula. So the name, the molecular formula, you should be able to interconvert those things. The weight, again, we figured out how to do that based on the molecular formula. This is the physical data. This is the state at room temp. And then I have this here. See these weird looking numbers? Let's see if we can make some sense of that. I'll let you do that on your own so you know how to do it. Again, so CH4, this would be C2, and then how many H's would that have? 6. C3, how many H's would this have? 8. So you can run through that, figure out the weights. So in the last couple minutes here, I think this is the last slide I'll be able to get to, but what does this mean? So see how it says C13 and 1H, again 13 and 1 are odd. Those are the nuclei that are observable in NMR. So that's what that nomenclature means. So the first number is the number of carbons, asterisks. The second number is the number of hydrogen sets. And then the stuff in the parentheses is the ratio of hydrogen in those sets.
Can you repeat that? Just like stuff in the top.
So methane has 1, 1, and 4. We see from the molecular formula there's 1 carbon, so 1. The hydrogens are all the same. So in our methane molecule here, there's 4 of them total. But again, depending on your reference point, if I rotate things, like this H is the same as that H if I rotate. So there's 1 set of hydrogens, and then in that 1 set, there's 4 total. But now look at ethane. See the molecular formula was C2H6. Why do I only have the number 1 there?
Because even if you swap the spots, they still occupy the same.
Yeah, so the response was if you swap them, you still end up with the same type of carbon. Another way of saying that is there's a mirror plane there. So even though there's 2 total carbons, the carbons are the same. And therefore, the hydrogens are the same, so there's 1 set and there's 6 of them total. See this number here, 1? There's only 1 digit reported in there. Now look at propane. There's 3 total carbons, 8 total hydrogens. Why is this number now 2?
Because the carbon with 2 hydrogens and the carbon with 3 hydrogens. Because the insulator has 2 carbons and the other 2.
So the inside carbon connects to the same type of group. So the mirror plane now is here. So that carbon and that carbon are the same. That's 1 type of carbon. This is different. It's bonded different. So that's the number 2.
So if you were to add like another CHH or another CHH, would it?
So let me just say, those are the subsequent slides. Let me just finish up this real quick because we're out of time. Why are there two sets of hydrogen? So you have CH3, CH3, CH2. So two sets. Now see how there's two numbers? 3 plus 3 is 6, and then 2. Now you're all experts in NMR spectroscopy. That's the concept behind it. Review the next couple slides, see if you can see where the logic's going.